Section 16.3 Pi electrons in conjugated molecules can be treated as moving freely in a box. In a conjugated molecule, such as 1,3-butadiene, the pi electrons are delocalized. They can move freely. The longest wavelength at which light is absorbed corresponds to the HOMO to LUMO transition. In a conjugated molecule, both HOMO and LUMO are often pi-type orbitals. HOMO is the highest occupied molecular orbital. LUMO is the lowest unoccupied molecular orbital. This table presents the apparent network length and a calculated network length for three conjugated molecules. They are all substituted polyene molecules. This is 1,4-diphenyl 1,3-butadiene, 1,6-diphenyl 1,3,5-hexatriene, 1,8-diphenyl 1,3,5,7 octatetraene. So let's look at this 1,3-butadiene first. You have 1,3-butadiene, 2 double bond, and the two phenyl groups are on carbon 1 and carbon 4. So carbon 1, 2, 3, 4 over here. What if you have 1,3,5-hexatriene, and then you just need to add another single bond and another double bond in the middle? Over here, one more single and double bond. What does this apparent network length mean? Well, this is calculated from the wavelengths, the longest wavelengths absorbed by this molecule. What's this calculated network length? Well, this actually refers to a simple summation of this 1, 2, 3, 4, 5 bond distance. All right, so from here, we are assuming the electrons can move from here all the way to here. So we sum up the length of these 5 bonds, and we will get this number. All right, now I'm going to show you how we got this number, 703.23 picometers. The longest wavelength absorbed by this molecule is 345 nanometers. I think this is in the ultraviolet region. Now we can just use this number to calculate the apparent network length. How? Well, if the molecule absorbs a photon, the photon energy is simply hc over lambda. The photon energy also corresponds to the difference between HOMO and LUMO, assuming this wavelength is the longest wavelength in the UV-vis spectrum. All right? And then we have HOMO, we have LUMO, assuming we have 4 pi electrons, 1, 2, 3, 4, there's 4 carbons, each contributing 1 pi electron. We have 4 pi electrons. We do not count this benzene ring or this benzene ring. We just assume the 4 pi electrons move around here. Then HOMO is level 2. LUMO is level 3. The energy difference is 3 squared h squared over 8 ma squared minus 2 squared h squared over 8 ma squared. So if you do this, it's 5 times h squared over 8 ma squared. And then on the left-hand side, you have hc over lambda. Therefore, we delete this h here. We change h squared to h here. Now, we can calculate this a squared. A squared is simply this by moving some of the terms around. And then we take the square root of this. We plug in all the numbers. 5 times the Planck constant. This is lambda of this photon. The wavelength is 345 nanometers, 8 m. This m is the mass of the electron. speed of light here, and then we calculate A. A is 723 picometers. This is the so-called apparent network length, calculated from the longest wavelength of the UV-vis spectrum of this molecule. We can also calculate the length of the carbon chain. Well, let's say the average carbon-carbon bond distance is 139 picometers. And then we have 5 such bonds, and then we get 695 picometers. So 1, 2, 3, 4, 5, assuming the electrons can move from this carbon all the way to this carbon. So 5 times the average carbon-carbon bond distance, we get 695 picometers. If you compare 723 and 695, I would say this is fairly close. You may also calculate the apparent network length for this 1,6-diphenyl 1,3,5 hexatriene with 6 pi electrons, or this 1,8-diphenyl 1,3,5,7 octatetraene of with 8 pi electrons. Again, we do not count the 2 benzene rings. All right. And then for your reference, I give you the longest wavelengths for these 2 molecules, 375, 390. What you can do is you just need to change this 345 with 375 or 390 nanometers, right? And also you need to change this number 5. Why is that? Well, this is because when you have 6 pi electrons, we need to have 4 squared minus 3 squared. The HOMO has a quantum number of 3. The LUMO has a quantum number of 4. If you have 8 pi electrons, they occupy 4 different orbitals or 4 energy levels, and therefore you need to change this to 5 squared minus 4 squared. Again, these are the equations to calculate the quantum number for HOMO and LUMO. If we have 8 pi electrons, they can occupy 4 different orbitals or 4 energy levels. So in HOMO is 4 if you have 8 pi electrons. And in LUMO is always in HOMO plus 1.